Hi, I will talk about feasible interpolation for sums of squares in polynomial calculus. So first of all, what is feasible interpolation? So it's a framework introduced by Krajicek in the 90s for reducing length of proofs lower bounds to lower bounds on computational models. So the basic idea is to translate a given refutation of a conjunction P and Q, sharing some sequence Z of common variables, into somehow efficient algorithm computing an interpolating function for the conjunction, and then use known computational lower bounds to obtain lower bounds on the proof size. So we say a function f in the variables z interpolates the conjunction if given an assignment to the variable z tells whether p or q is unsatisfiable when z is replaced with the assignment a. So this idea has been used to prove lower bounds, for example, for resolution and cutting planes from lower bounds on monotone Boolean and real circuits respectively. These are the so-called monotone feasible interpolation properties of the two systems. On the negative side, under some reasonable cryptographic assumptions, neither Frege nor extended Frege systems can admit feasible interpolation. And this is with respect to polynomially sized Boolean circuits. Okay, so let's next look at the proof systems that we consider here. So first, polynomial calculus. So polynomial calculus is a proof system to infer polynomials from polynomials in a step-by-step fashion, similar to traditional propositional proof systems. So a proof is a sequence of polynomials, such that the last polynomial is the polynomial that we are proving, and each polynomial in the sequence is either an axiom or obtained from previous polynomials by one of two inferential rules. So we have the lift rule and the linear combination rule. So a proof is a certificate that polynomial P is in the ideal generated by Q. And thus we call a proof of constant polynomial 1 from Q a polynomial calculus refutation of Q, since this shows that there are no common roots of Q even in the algebraic closure of F. Do note that here we do not assume the presence of Boolean axioms, and we work in this more general context for polynomial calculus. However, for sums of squares we do work over the Boolean cube, and accordingly we look at polynomials over so-called twin variables. So the intended meaning here is that all variables take values 0 or 1, and the two variables in a pair of twin variables assume the opposite values. Okay, so in this context, a sums of squares proof of non-negativity of P from Q is an equality of the form P equals some sum of squares plus some lifts of the axioms, and this equality is taken modulo the Boolean cube. So such a proof is a certificate that P is actually non-negative on all the 0, 1 roots of Q. And accordingly we call any proof of non-negativity of -1 an SOS refutation. So here we prove the feasible interpolation property for both sums of squares and polynomial calculus in a rather strong form. Namely, we show that not only is the interpolating function computable in polynomial time in terms of the size of the given refutation, but one can actually find a refutation of one of the constants in polynomial time in both cases. Okay. Both proofs follow a similar kind of pattern. So first we give what I call semantic characterizations for proof size. So some kind of a mathematical object that captures a suitable class of proofs and thus gives a semantic description of those proofs. Secondly, using these characterizations, we prove the so-called feasible disjunction property for the systems. So feasible disjunction property is a property related to feasible interpolation, but understood here as an existent statement about the existence of a suitable proof. And finally, we show that this proof, whose existence is guaranteed by the feasible disjunction property, can actually be found in polynomial time. So let us look at polynomial calculus first. So first we'll define the class of proofs that we are looking at, and this is what I call proofs over a set of monomials. So what is the motivation for this definition is the following. So in the feasible disjunction property, we want to prove the existence of a suitably small proof, but we do not want to prove upper bounds directly. Rather, we prove the existence of a proof over some small set of monomials. And why is this? Is because the set of all polynomials provable over some set of monomials has a particularly nice structure. Namely, it's a linear subspace of the space of all polynomials. And this nice structure gives us more tools to develop these semantic characterizations for the set of proofs. Okay, so here let S be any set of monomials containing all the monomials in the set Q and the empty monomial, that is the constant polynomial 1. And let S hat be the set S together with all the lists of X, S with a variable. And we say that a polynomial calculus proof is over S is if any polynomial in the proof is a polynomial over S hat, and the lift rule is only applied when the antecedent is actually a polynomial over S. Okay. And we denote like this the space of all polynomials that have proofs from Q over S. So as a semantic counterpart for proofs over S, we introduce what I call the reduction operators over S. So a reduction operator is a linear and idempotent function from the polynomials over S hat to itself, satisfying the following. So it maps the constant polynomial 1 to 1, each axiom to 0, and satisfies this following kind of a distribution property. So I want to mention that similar objects have been used previously to prove degree lower bounds in polynomial calculus, originally by Rasborov. We have here restated these definitions in the context of proofs over a set of monomials. Okay. So these reduction operators over S, they capture the provability over S in the following sense. we have the following soundness and completeness theorem for these operators. That there is no refutation of Q over S if and only if there is a reduction operator for Q over S. So in proving lower bounds, one uses the soundness property. So constructs a reduction operator that shows that there is no refutation. We will, however, argue the opposite way. From the non-existence of a reduction operator towards the existence of a refutation. Okay, so this is what we do in the feasible disjunction property for polynomial calculus. So here, P and Q are two sets of polynomials in a disjoint sequence of variables. So if we were given a refutation of P union Q, look at the set of all monomials appearing in this kind of refutation. We know that there is either a polynomial calculus refutation of P over the projection of S to the variables X, or a polynomial calculus refutation of Q over the projection of S to the variables Y. Okay, and how to prove this is as follows. So supposing towards a contradiction that neither refutation exists, we have these reduction operators for P and Q over Sx and Sy respectively. And using these two reduction operators, we can define a third one for a larger set of polynomials. So let S prime be the set of all products of an element of Sx hat and Sy hat, and do note that the original S is a subset of S prime, and define a linear function from all the polynomials over S prime as follows. So using Rx and Ry as components here. So now this R has some very nice properties. First, it maps constant polynomial 1 to itself, because the two components do. It maps all the axioms to 0, and it inherits this distribution property from its two components. So it's not hard to see now that the existence of such R is in contradiction with the assumption that in the given refutation only monomials from the set S appear. Okay, so now we want to argue that we can find the proof over some set of monomials in size, in time polynomial in the size of S. So this claim we do only for finite fields. So to do this, we generate a basis for the space of polynomials provable over S, and also polynomial calculus proofs for the basis elements in time polynomial in the size of S. And this basis will have the following very nice property, that all elements in the basis have distinct leading monomials. And using this property, it is very easy to check whether some polynomial is provable from Q over S, simply by reducing P with respect to B. Okay, so on this slide we have the pseudocode for the algorithm to generate the basis. So one can pause the video and convince yourself that that this is correct. So as a consequence for the feasible disjunction property and the polynomial proof search, we get the feasible interpolation for polynomial calculus as stated. Okay. So now, secondly, we look at sums of squares. So we use again the same idea of looking at proofs over some set of monomials. So we say that an SOS proof is over set S if the sum of squares is actually a sum of squares of polynomials from so polynomials over S, and each lift of an axiom is also a polynomial over S. Additionally, we need to look at explicitly bounded proofs for the proof search later on. So we call the proof proof R bounded if all the coefficients in the lifts of the axioms are bounded by R in absolute value. Okay. And we do, at this point, we do not yet bound the other coefficients in the proof. So the coefficients in the sums of squares part or in the Boolean part for technical reasons that I'll come back to. Okay. So as a semantic counterpart, we introduce what I call epsilon pseudo expectations. So a linear functional from a set of polynomials over S squared is an epsilon pseudo expectation for Q over S if it satisfies the following conditions. So it maps constant polynomial 1 to 1. It maps any square over S to something non-negative. It respects the Boolean ideal, and it maps the lifts of the axioms by an element of S to epsilon close to 0. So again, similar objects are standard to prove degree lower bounds in sums of squares. And we've just restated these for proofs over sets of monomials. Additionally, the fourth item on the list is usually stated in the form that E of MQ should be equal to 0. However, this is the form to argue against bounded proofs. This is the correct form to argue against explicitly bounded proofs. Okay. So the following two lemmas give the connections between these bounded proofs over S and epsilon pseudo expectations over S. So first of all, if there is an epsilon pseudo expectation for Q over S, then there is no R bounded refutation over S for a suitably small R. Okay. This is a very easy exercise to see, basically. Additionally, we have the completeness property, so that if there is no R-bounded refutation, then there is a suitable pseudo expectation. So it is in this part where we need the Boolean axioms. Actually, what we need from the Boolean axioms is that the cone of all polynomials, provably non-negative, just modulo the Boolean axioms, admits a so-called order unit. So that is basically the route to generalize this statement if needed. Additionally, in this proof, we need that we did not bound the coefficients of the sums of squares part original, and only the lifts of the axioms. Okay. So again, using completeness, we can prove the feasible disjunction property for sums of squares. So again, given an R-bounded refutation of P union Q, and look at all the explicit monomials in the refutation. So what I mean here is that the refutation written explicitly as some polynomial squared plus some polynomial squared plus some polynomial times an axiom plus some polynomial times a Boolean axiom. The explicit monomials are just all the monomials that you can see there. So the monomials inside the squares, the monomials in the lifts, in the axioms, in the lifts of the Boolean axioms, and in the Boolean axioms themselves. Okay. So from this information we can define a new bound, this R prime, and show that there is an R prime bounded SOS refutation of P over Sx, or an R prime bounded SOS refutation of Q over Sy. And the proof here is very similar as in polynomial calculus. So assuming that neither proof exists, we have these 1 over R prime pseudo expectations for P and Q. And using these pseudo expectations, we can define a linear functional on the whole space of polynomials over S squared that has particularly nice properties that map 1 to 1, that map all the squares over S to something non-negative, map all the lifts of the Boolean axioms in the given proof to 0, and map the lifts of the non-logical axioms close to 0. So again, similarly as in the soundness proof, such existence of such a functional is in contradiction with the assumptions about the given refutation. Okay. So now, for a proof search, we use the ellipsoid algorithm, and here the explicit bound on the coefficients was important to narrow down the feasible region to guarantee a polynomial runtime for the search. So there's two steps to this argument. First of all, use the bound on the list of the axioms to bound all the coefficients in a refutation. So this is some linear algebra, and then formalize the search for a refutation over S as a semi-definite program whose feasibility can then be tested in time, polynomial in the size of S and logarithm of R. Okay. And as a consequence for this, we get the feasible interpolation for SumsofSquares as stated here. Okay. So finally, for the conclusions. So first of all, our results do not yield new lower bounds for these systems, but they do give new information about the relative strengths of the systems considered. Secondly, we did not consider the proof system Shirley-Adams here, but a very similar proof as with SumsofSquares gives a feasible interpolation also for Shirley-Adams. Okay. Thirdly, question about the monotone feasible interpolation. So if the interpolating function is a monotone function, is there always a way to transform a short proof into a small monotone Boolean circuit computing the function? For SumsofSquares, we know that this cannot be the case. This is because SumsofSquares has short proofs of the click coloring formulas. But it is open whether polynomial calculus or Shirley-Adams may admit monotone feasible interpolation. And finally, is this the ideas here used to prove the feasible disjunction property for the systems useful for proving feasible disjunction property for stronger systems, even for systems that we know cannot have feasible interpolation? Okay, so, oops. Thank you for your attention, and bye.